So the plan for this video is to walk through and explain the formulae and their corresponding diagrams for these increasing annuities, these 4 types of increasing annuities. Then I'm going to go through some common complications that I think might aid your understanding. And then finally 2 examples from the IFOA exams, which is the UK's Board of Actuaries. Okay, so this first one here is a simple increasing annuity in arrears, and this formula is the present value for the annuity that looks like this. So if this is the start of our time period, or the time that we are present valuing all of these payments to, then our first payment happens 1 period after that, and likewise second payment 2 periods after that, end payment in periods after that. Now, what happens is there must be a constant increase in the size of each of these payments. So in other words, this payment minus this payment should be the same as any 2 consecutive payments, the difference between any 2 consecutive payments. Okay, and also an important thing to note is that this first payment should be the size of that increase. So if you ever have cash flows that look like this, then you'll be using this formula. And this formula is a present value of an level annuity in advance, and you subtract from that the number of payments times by v to the power of n, and in the denominator we divide by the interest rate relevant for the time period. Now, that is very similar to the denominator that you would have in a level annuity in arrears. So this annuity here would have 1 minus v to the n, and the denominator would also have I. So you can note that similarity. Just aid your understanding, or rather make it easier to remember. Now, this second formula is the exact same concept, except our first payment starts at time 0. Then in the denominator, we have d, which is 1 minus v, which is the same as in our denominator of our level annuity in advance. So that 1 minus v equals d, which is the same denominator. Okay, so that deals with the simple increasing annuities. So let's move to the piecewise continuous increasing annuity, and which is this one here, and then just the increasing annuity. So this piecewise continuous increasing annuity has a similar fashion to the first ones, where the difference between consecutive payments or consecutive payment sizes is constant. So instead now of me saying consecutive payments, that doesn't really make sense because it's continuous. So what I would then say is between consecutive segments of continuous payments. So in other words, the height of that minus the height of that would be the same as the height of that minus the height of that, and that constant difference in height is the same as the height of our first continuous payment. So this height here, going off of that, would be x, and then the height of the third continuous increasing segment would be 3x, and obviously they increase by x as you move along. And within this first time period, we have a level annuity that occurs for 1 time period, a continuous level annuity for 1 time period, and that happens between each of these time points. Okay, and then once again, our numerator is the same. So you'll note that in all 3 of these, they have the exact same numerator. And our denominator has changed to be delta the force of interest, which you'll know matches the denominator in our continuous level annuity, which is, the formula has 1 minus v to the n to the over delta, and this delta force of interest same, so that helps you remember that as well. So it's not actually much to remember if you realize that the denominators mirror the level annuities and the numerators are mostly the same, except when you arrive to this final increasing annuity, which has only this term different in the numerator. So there are two types of continuous increasing annuities, this piecewise increasing annuity, as well as the simple, or maybe not simple, but just the continuous increasing annuity that starts from 0 at time 0 and increases linearly. So the formula for this still has that force of interest in the denominator, reflecting the level annuity, the continuous level annuity's denominator, and then the numerator. Only difference is instead of having this level annuity in advance, we have, or simple level annuity in advance, we have a continuous level annuity. Okay, and then this formula should represent this. So the things that you need to have for this to work, this formula to work, is a constant increasing payment, and then it must start from time 0. It must start at 0 at the start, okay, to the point that you're present valuing it to. Okay, now you could also use this formula for this present value. It would effectively be the same thing, and then once again here, the continuous payment streams formula would have to be a linear function. So it's a function of time, and then it would have a constant gradient, and then this plus c would technically be 0 as well if you started at time 0. And then this vt is just present valuing each of those points in time to 0, and we integrate from 0 to x because it's a continuous payment. But if you don't understand this, don't worry, you can go watch my video on continuous payment streams. Okay, so let's move over to some common complications. So the first one, these are all present value formulae. Now what happens if we need future values? So there are formulae for the future values, but most of them are just future valuing the present value formulae, and I really don't think there's much point in showing you those formulae. So I just recommend you know the present value formula, and if you ever ask for future value, just calculate the present value first and then future value it afterwards, so that you don't have to complicate your life and you're working with formulae that you know. Okay, then what do we do if we need decreasing annuities? Okay, so it might happen that you're asked to calculate the present value of some decreasing annuity or even future value, but you might have to make a calculation that involves a decreasing annuity, but you only know these formulae for increasing annuities, and there are formulae for the decreasing annuities, but why learn those when it's really not that much extra effort to just change your understanding slightly? And it's not actually part of the curriculum anymore, as far as I'm aware, to know the decreasing ones, but you might still need to calculate a decreasing annuity using the increasing annuity. So what do I mean? Okay, so if you had a timeline like that with time 0, time points going on, now what we know is when we have increasing annuities that look like that, constant increase, and that constant increase is the same size as the first payment. Now we want to know, how do we get a decreasing annuity? So what you'll notice here is that the difference between a level annuity at that point, if we subtract this increasing annuity, we'll actually end up with a decreasing annuity. So what I mean is, a level annuity would have a payment like that, would have payments like this. And if we subtracted the two from each other, what we'd end up with is this payment. We subtract this level annuity. So from this level annuity, we subtract the increasing annuity, which has a payment of 0 at time 0. So we have time 0, 1, 2, and 3. And our payment would be that size. Then at time 1, we would be subtracting this white payment from this green payment, and would be ending up with something like that. And at time 2, we'd be subtracting this white payment from this green payment, would be left with the difference, which would look something like that. And then obviously at time 3, the payments are equal, so when we subtract them, we end up with nothing. And here you can see that we've ended up with a decreasing annuity. And you just have to be clever with this. So in terms of whether you're using annuities that are in advance or in arrears, so that you don't end up mixing up the payments, and then which level annuity you're going to use and the height of that level annuity, depending on whether you used a increasing annuity in advance or in arrears or however you did it. There's lots of ways to do these types of questions, but just be aware of that. I'm going to show you some examples so that'll help out. And the same logic applies for these other types of annuities as well. So you might want a decreasing annuity, a piecewise continuous decreasing annuity, and then you'd take a level annuity over a certain period and subtract from that the increasing annuity, which would leave you with those level continuous payments, which are decreasing. Okay, and then obviously the same works for this. If you subtract from this level annuity, this continuous increasing annuity, you'd be left with something like that, which is decreasing as well. Okay, so what about compound increasing annuities? So this is a good question. Now, these annuities that I've been speaking about are strictly when the gaps between the payments or the increase in payments is constant. So if they compound increasing annuities, these formulae no longer apply. So what we use then is just first principles. So we might have a payment, so compound increasing could look something like this with a payment like that. Then the second payment slightly bigger, the third payment slightly bigger than the last one was bigger, and it keeps getting increasingly large in a non-linear fashion. So very much a compound increasing fashion, exponential fashion. So we don't use the normal increasing annuity formula, and instead we incorporate this growth rate of the payments into the interest rate. So what happens then is this first payment doesn't get present valued and it doesn't get grown, and this second payment here gets grown by the growth rate of 1 plus G, and it gets discounted by the discount factor V. The second payment gets grown twice, 1 plus G squared, V squared, etc. And what happens then is we group these 1 plus G times V into a new variable called W. And this formula with the W's ends up being a new annuity formula, a level annuity formula that takes the form A dot dot N. So a level annuity in advance. Okay, and obviously it doesn't necessarily have to turn out to be a level annuity in advance. If this happened to be, this payment didn't exist, let's say, then it could be level annuity in arrears. That's really not important, but the method is the important way to figure out what to do if we're given compound increasing annuities. Okay, so let's read this last question here. What if the first payment is not the size of the constant increase? So I kept emphasizing that our first payment has to be the same size as the difference between any two consecutive payments. Now, what happens if that is not the case? Or what happens if this annuity doesn't start from 0? Or what happens if this jump here, the height of the first continuous annuity is not the same as the difference between the heights of consecutive level annuities, the difference between their heights? So what happens then? So what happens then is we simply incorporate other annuities into our formula so that we can work in terms of this first payment being of that same height of the increase. So I'll use an example to explain this. If we had a timeline and our first payment at time 0 and so on, so our first payment, let's say it was that high, and our second payment slightly higher, third payment slightly higher than that, and the fourth payment at time 3 slightly higher than that. Now, what I'm intending to show with this diagram is that that distance is the same as that distance, is the same as that distance, but the first payment is not equal to that height. So what do we do here? So we simply cut it off there, and this part of our payments will represent a standard increasing annuity that we know. Sorry, that shouldn't be 3, that should be a 4. In advance, and this part of it will simply represent an annuity in advance for 4 payments, a level annuity in advance for 4 payments, and then we take the sum of those two to get the present value. Okay, so let's move on to some examples now. So the first example, a loan is to be repaid by an increasing annuity. The first payment will be £100, and the payments will increase by £50 per annum. Payments will be made annually in arrear for 10 years. The repayments are calculated using a rate of interest of 5% per annum effective. Calculate the amount of the loan. Okay, so I've drawn a timeline to help us understand what's really going on here. So our first payment at time 1 is 100, and our second payment at time 2 is £50 more than that at 150, and that increases all the way until 10 years later. It says in arrears for 10 years, where we receive some payment of unknown size that we can work out but don't need to, so choose not to. You'll see in the formula that you don't actually need the size of that payment, but that won't always be the case, but in this case we don't need it. So the way that we're going to do this, as I said for my explanation of this question, what if the first payment is not the size of the constant increase? You see that's the case here. Our first payment is 100 and our constant increase is 50. So what we do is we split it into a level annuity and an increasing annuity. Now, these payments represent this simple increasing annuity in arrears with that constant difference of 50, the first payment also being of size 50, and we have 10 payments, and then this level annuity is simple enough. Now, present value is simply the sum of those, so you write out your formulae, you plug in the interest rate, plug that into your calculator, and you end up with the answer of £2,354.78. Okay, so let's move on to this last example. A company has agreed to build and operate a ferry service for a regional government. The company will invest $10 million at the outset and a further $8 million after 1 year. The ferry will then come into operation and the company will receive payments at the end of each year, the first payment occurring at the end of the second year of the project. The amount of payment at the end of the second year will be $4 million, increasing by $0.5 million in each of the subsequent years until the annual payment is $7 million, after which the payments will reduce by $1 million each year. When the payments have reduced to 0, the company's involvement in the project will end. Calculate the net present value of the project at a rate of interest of 6% per annum effective. Okay, so the formula for net present value is the present value of inflows minus the present value of outflows. So our outflows are simple in this example. We have the company investing $10 million at the outset and a further $8 million after 1 year. So I'm doing all my calculations in terms of millions so that I don't have a large number of unnecessary zeros complicating my working out. So this first payment doesn't get discounted, it happens at time 0. And then this payment of 8 million happens after 1 year, so I discount it by V. Okay, now let's address the present value of the inflows. So we read here that the amount at the end of the second year will be $4 million, and that increases by $0.5 million in subsequent years until it reaches 7 million. So what we have here is it starts at 4 million at the end of the second year, and it increases by 0.5 until we reach 7 million at some certain time point which we have to work out. There's 2 ways to work that out. This way is the simplest way, and because there's a few number of payments, I'd probably recommend you do it. So the way that I do here is simply increasing the payments. So we start with 4 million, goes to 4.5 million, then 5, all the way up to 7, constant increase of 0.5 million. And this payment of 4 million happens at time 2. The payment of 7 million happens, if we simply count up, 2, 3, 4, 5, 6, 7 at time 8. So that's how we get that 8. Now, if there were a large number of payments, this might take you an unnecessary amount of time. So it might be useful to remember or to intuitively think through a way to calculate that time point. And this is how you do it. So you need to reach 7 million and you're starting off at 4 million. So you need to go up by a difference of 3 million. Your payment size is only 0.5. So 3 divided by 0.5 means that you're going to have to make 6 payments. So you're going to have to make 6 payments, and you're starting at time 2. So you must add 2 and 6, and you get 8. Okay, so those are the 2 ways that you calculate that 8. Then we're told that after which the payments will reduce by 1 million each year. So that's simple enough. We go from 7 to 6 to 5 all the way to 0 at time 15. Okay, so now that we have an understanding of what the cash flow looks like, we can go ahead and try and figure out a relevant present value formulae. But before we do that, we're going to have to use these diagrams to help us understand what's working. Now, obviously, you don't actually have to go and draw these diagrams out just to illustrate the understanding, but you're going to have to do some thinking to figure out which annuity formulae you want to include in your present value equation. Okay, so what we can see here is that we're really dealing with 2 parts. We're dealing with something that increases until time 7 and then decreases beyond that time. So that's a logical place to split it. Hence these 2 big curly brackets. Now in this first portion, this first period from time 0 to time 8, our increase is constant at 0.5, but our first payment starts at 4. So what we then do is we split it into an increasing annuity and a level annuity. Now, beyond time 8, it's a decreasing annuity. So this is an example where you would have had to have known a decreasing annuity formula, but because you know how to work with your increasing annuity formulae, you're going to work around that by incorporating another level annuity and simply subtracting your increasing annuity from your level annuity as such in a fashion like this. Okay, so let's move over to this present value equation and try and understand how we've got these specific values for the payments and what annuities we've included and why the certain amount of payments in each annuity. So this first line here is dealing with up until and including the payment at time 7. So that's excluding this payment of 7 at time 8. So what we have here is a level annuity of 3.5, and that'll occur throughout this. So we'll have 3.5 plus 0.5 for this payment, all the way up to the payment at time 7, which has a value of 6.5, which is 3.5 plus 3. So this 3.5 is the level annuity that will remain throughout, and that happens for 6 payments. That makes sense because we have 7 minus 1. Okay, so not minus 2, don't make the mistake. If you take 7 and you subtract 2, you're effectively excluding the payment at time 2, and you're only counting 3, 4, 5, 6, 7. But we need to include the payment that happens at time 2, so we take 7 minus 1, which is 6 payments. Okay, so that's how we get that 6 there. Now, in our increasing annuity, the number of payments should always match. Okay, so we have an increasing annuity in arrears, simple increasing annuity in arrears for 6 payments, and that's of 0.5. Does that make sense to me? So it starts at 0.5, and our 6th payment must be 6 times by 0.5, which is 3. Yes, that makes sense. Okay. And then something also to note is by using these formulae, we've been present valuing it to this time point at time 1. So we had a level annuity in arrears, which present valued all of those payments to time 1, and then also this increasing annuity in arrears, which present values them to time 1. We want the present value at time 0, so we must discount them by another year. Okay, now dealing with the time beyond 8. What we're going to do here is we're including payments from time 8 all the way up until the last payment that occurs at time 14. Okay, and the first payment is of value 7. So what we're going to do here is, you could have done this in a number of ways. So you could have taken an annuity, a level annuity in arrears or in advance, and then your increasing annuity would have changed as such, or vice versa. But the point is, there's a large number of ways that you could have gone about this, and it doesn't necessarily mean that they're wrong or right, just depending on whether you executed it correctly. So I'm going to show you one way, and you can go ahead and try different ways and see if you get the same final answer as me. Okay, so the way that I've done it over here is we used a level annuity in arrears for 7 payments, and that level annuity is of value 8. So each payment will be of $8 million. So that is one more than the payment that happens at time 7. And this is in arrears. So what you note there is that it discounts it 2 times 7. So we have this v to the 7 outside here, which will discount all of those payments back to time 0 from time 7, even though that our payment of 7 occurs at time 8. Okay, so if we have this level annuity of 8, what increasing annuity are we going to have to use to subtract from that to get the correct decreasing annuity? So obviously, if our first payment is 7, but our first payment in our level annuity is 8, it's going to have a constant increase of 1, which is why the coefficient of this increasing annuity is 1. Now, 7 payments, I've said that they always match, so that makes sense. Now, why is it 7 though in the first place? So obviously, it makes sense to be 7 because it has to reach 0, and beyond that, the company is no longer involved in the project, so there's no payments. So it decreases from 7 all the way down to 1, which is 7 payments. Okay, so that's why we have that number 7 there. Okay, and then, yes, I've explained that coefficient of 1. Okay, so then all that we have to do is plug in values into our formulae, into our calculator, and arrive at a final answer. And I'm not going to bore you by doing any of that or explaining these numbers. I'm pretty sure it's obvious from there. Okay, so I hope you enjoyed this video and found it useful. And if you did, please don't forget to leave it a like and subscribe to the channel. Thank you for watching.